Hello and welcome to the 11th part of a series of videos aimed at developing retro games in vanilla JavaScript using the canvas element. My name is Anthony and please join my corner of the web where I'm currently building a StreetFighter game within the browser using the latest technologies. So far we've been developing our game from a single main class, meaning it has the sole responsibility to know and manage the dependencies for the game, such as all the entities. As we've only been working on the stage screen for the video series, we probably could continue to work that way just fine. Although, if we wanted to add a title screen for example, how would that work? The entities the class manages have been working independently from each other, meaning we currently don't have any way for them to talk to each other. At some point we're bound to need our entities to send data between them. So how does that work also? With those questions in mind, let's again bring up our dreaded to-do list and scroll through it, pulling out the necessary items we're looking to tackle in today's video. We'll first introduce a scene system into our game code to decouple the main game loop responsibility from all the actual screens a StreetFighter game could potentially have. We'll talk about why this is a good thing, along with exploring how this could be applied and extended further. Next we'll delve into the global state, or store, objects, to hold common sets of data which can be accessed and shared across the entire game. We'll explore one way to implement this, using a couple of the fighter's properties. In fact, this will be the main area of focus for us today, as we know we need to share their data in multiple places, but primarily in the status bar for such things as the health bars and the scores, which fully enough is another thing we'll look to tick off today, along with making the KO sign flash when the health is below a certain threshold. So yes, we'll have a nearly complete status bar HUD by the end of the video. Finally, we'll look to add the hit splash graphics and animation based on the global state too, picking up the attack collisions where we left off in the last video. So again, another packed episode today. And just before we get on with the video, I would like to kindly ask people to click the like button, especially if you find these videos helpful in any way. I noticed that over 70% of people who watch my videos are unsubscribed too, so why not go ahead and do that if possible. Both are absolutely free and will only help to grow this channel, and ultimately give me more emphasis to focus and improve on its content. For those of you who have already done so, either on this video or any of the others, a big thank you goes out to you, as it's extremely appreciated. Okay, let's jump right in. We'll start today's video by considering how we end most of our videos in the series, with some refactoring. Let's first open the main StreetFighter class and have a quick review of what it's currently doing. As we scroll down, you can see that it has the standard constructor, the draw and update functions, along with the main loop and start functions at the bottom. Moving back to the top of the class and its constructor, here we manage a number of entities too, such as the overlays, fighters, their shadows, and the background stage and its camera. These entities are all required to set up the battle and stage. As you can see, at the moment we have all our game setup, configuration and main game loop all within this class. To be fair, this could be fine for smaller games. Although, if we were to cater for all the screens Street Fighter 2 has to offer, then this can become unmanageable very quickly. Ideally, just as we've done before, we should look to separate this complexity into their own classes or modules. The most common term for these screen classes is scenes. So what actually is a scene? Basically, a scene is a section of a game that encapsulates everything required to manage a particular section of the game. How and where you divide your game into sections can be personal preference, but generally, at least from a personal point of view, this is whenever a background image or screen changes. To delve into this a little deeper, let's take a look at what we currently have today first. I'm going to say we're building the fundamentals of what we'll call the battle scene. This is obviously where the bulk of the time and gameplay is spent in Street Fighter, and it's the responsibility of this scene to load the necessary stage and fight entities depending on the currently defined player selection and battle rotor. We'll explain a little more about this later in the video, but for now let's take a step back for the moment and have a look at other scenes we could potentially define for the game. We know before every fight we have the versus screen, which gives us the visual presentation of the fighters looking to battle it out. Then before that is the player select screen where the player or players choose the fighter they would like to use. And before that is obviously the title and attract demo screens. We'll also throw in the battle or result screen at the end too, for a complete end-to-end overview. As you can see, we have multiple screens we can split up into scenes or classes. So how do we manage the loading and unloading of these scenes as we move from one to the other? Well, as we can only realistically interact with one scene at a time, we need to know which scene is the current one. So, as this needs to be controlled and known from a game level, rather than at a scene level, we'll store the instance of the current scene at the top level, which for us is the Street Fighter class. Any shared data will be held in the game's global state however. I'm sure you're now asking what do we mean by the game's global state? Well, hold that thought for a second. Let's first look at decoupling the current battle scene code from the main Street Fighter class code by moving it into its own class. This will separate those concerns, leaving the main Street Fighter class to be only responsible for maintaining the game's setup and main loop. Back in the Explorer window, let's first create a new folder called Scenes to hold any potential scene classes we'll have for our game. Inside here we'll create our first scene class called Battle Scene and proceed to add the standard code scaffolding such as the constructor. As a first pass, we'll copy over the original code from the StreetFighter class to this one and refactor as necessary, starting with the initial variables such as the overlays and stage. For the fighters though, let's wrap the current code within its own function called getFighterEntities. We'll expand on this later, but for now it's a good way to keep the logic contained. Next we'll add the usual update and draw functions to house our logic and drawing calls. Then referring back to the original code, we'll further break that down to smaller functions to house the necessary code, keeping it clean. In our main update function, we'll also make a call to these new functions. Jumping back to the constructor for a second, we'll now set up the scene camera and fighter shadows. The one slight snag with the camera however, is that we no longer have access to the context in the constructor, so we'll just replace the code with a hard-coded value of 192 for now, which we know is the screen width divided by 2. Another one we'll add to our to-do list for later. Before moving on though, we'll add the remaining calls to the main update function. Finally, we'll then copy over the code into the necessary new stub update functions. We'll now perform the exact same process but for the draw functions. Again, creating the initial stub function blocks, then calling them within the main draw function. And finally, migrating the original code over to these new functions. With all those in place, let's now start cleaning up the StreetFighter class. We'll first remove all the contents within the constructor and also remove both the update and draw functions. Notice how we've left their calls within the frame function. Within the constructor, we'll create a new instance of the battle scene class and assign it to the local scene property. Then back in the update and draw calls, these will now become the update and draw calls for the scene instance. Obviously we'll need to pass on the necessary frame time and context objects though, so that they are forwarded on to the necessary dependencies. Lastly, we'll remove any unnecessary imports too. And there you have it. The StreetFighter game class now simply manages the game setup, which now includes the scene instance and the main game loop, and nothing more. Whereas the battle scene class now houses the code to manage the current game code. Just before we test our refactor, it seems we're missing a couple of things in this class, so let's fix those first. We'll start by adding the missing overlay imports. Then in the getFighterEntities function, we'll update the migrated fighter references to use the new fighterEntities array instead. Looks like we're also missing the constant imports for the camera, and also the entities array too, so we'll add those. And finally, the camera update function is missing its context parameter. And hopefully, we should be golden. Let's go prove that by checking the browser. Thankfully, with those last few tweaks, it seems everything is working as intended, and we're back to where we were at the end of the last video. The difference now though, is that we've now decoupled the game container code from the game logic code, making the overall code easier to extend moving forward. So now let's come back to the question about global state. What is it and why do we need it? In general terms, this state is a persistent data store that can be accessed by any or all of the scenes, because it sits at the top level or in the global space of our game. This means it's long-lived and will usually be in memory for the whole time the game is running. For that reason, it's best practice to keep this data store as small as possible, containing no more data than what is required across all of our game. It also has a downside in that any object which has a reference to it can in theory mutate it, unless we specifically add measures to guard against it. There are multiple ways to tackle that, but we'll leave this topic for another video however. Ideally, state or data is better kept closest to the code that requires it, for example in scenes or entities, especially for state that is short-lived. This will save on memory and honestly, maintenance, removing possible debugging headaches later down the line. In terms of our StreetFighter game, we're going to use the global state to store the data for our currently selected fighters, and their specific data. Knowing which fighter is currently in play is required across multiple scenes within StreetFighter, so it makes sense to hold it there. As for the fighter state object, this will hold the fighter ID, their score, and the number of battles they have played. Eventually this could hold several other details, such as the number of battles won, their list of defeated opponents, how many continues they have left, and possibly their control scheme to name a few. Either way, we'll be using the JavaScript module system to store the state object, as this will keep it out to the browser's global space at least. Back in the code then, we'll first create a new folder called state. Inside here we're going to create two new files, one to hold the game's global state object, and one to hold the fighter state object. We'll name these game state and fighter state respectively. Starting with the fighter state module file, we'll first create a new exported function called create default fighter state. This will take an ID, which will be the ID of the chosen fighter. This in turn will return an object with that ID, a score which we know defaults to 1, and battles to hold the number of battles they participated in. Before we move over to the GameState module, let's first open up the fighter constant file and create a fighter ID enum object and add both Ryu and Ken's IDs to it. This is to be used for the ID property in the fighter state function we've just created. Okay, with that now available, back in the GameState module, we'll create a new exported object called GameState, funnily enough. We'll only add the fighters array property for now, but we'll extend this as the series continues. We'll now add two calls to the create default fighter state function and pass on the required Ryu and Ken fighter IDs. Obviously, if we were to do this properly, these IDs will probably come from the fighter select scene. To put the game state to use, let's open the status bar overlay entity. Notice how we're passing in the fighter entities into the class's constructor. We do this to get the name of the fighters, but we should probably use the fighter IDs from the game state object moving forward, to keep it consistent. Let's first remove the constructor arguments and local property. Then at the bottom of the constructor, we'll refactor the code to do just that, and pull the names from the GameState object instead, this time using the array's map function. We can now also remove the name property from our fighter classes too at this point, again for consistency. So in both the Ryu and Ken classes, we'll remove the first parameter from the supercall, and subsequently remove the name property from the fighter class. However, removing this property will affect the collision code and console message we added in the last video, so we'll fix this and again use the GameState fighters property instead. We'll use the fighter class's player ID property as an index to the array to obtain the enum string property. We'll do the same for the opponent's name too, following the same principle. And there we go, the console message should now produce the same result. As we're normalizing all of the things to use our GameState object, let's do the same in the battle scene class too. Until now we've always manually created the fighter entities by newing the Ryu and Ken classes directly, but let's use the GameState here too. In the getFighterEntities function, we'll replace the entity array with a map function, so that we can iterate over the GameState fighters array instead. Inside this we'll call a new mapping function called getFighterEntity, and bind it to this class. Let's create this function next with a fighter state and index parameters, as we know the map function will forward these on. This function will return a class instance of the fighter, but we only know the fighter ID at the moment. So let's create another function called getFighterEntityClass, which will match this ID to the fighter's entity class equivalent. We'll do this with a simple switch statement, and by default make it throw an error if the ID is not recognised. Notice how we're only returning the class reference though, because back in the getFighterEntity function, we'll be returning a new instance of this class back to the original map function. This is a little long-winded, I agree, but it makes the code much cleaner, and it's now able to accommodate any fighter we throw at it if we wish to extend the fighter rotor. Okay, at this point I think we made enough refactors to warrant a check of the browser to see if everything is still working. And thankfully, it seems so. Both Ryu and Ken are able to move and attack as per usual, and the console message is still logged when there is a collision. Okay, so we're now over 10 minutes into the video, and we've done quite a few changes to the code, and I'm sure some of you are saying we haven't made any progress on the game. While this is true, hopefully you'll agree the code is now far more scalable and cleaner. It's always wise to take a step back from your code once in a while and decide to perform some refactoring, especially as your understanding of the code and its direction evolves over time. This is why I tend to do this at the end of each video, to keep that mindset. That said, the main reasoning for this was to make the GameState object available, so we're now able to move forward and implement the next changes to the status bar entity. Towards the end of the last video, we had the basic elements of the fighter attack collision. Currently the response for this, as we've just seen, is the message we send to the console with the collision details. As you can expect, we'd ideally rather have the fighter take damage instead. This is usually presented by the health decreasing for the fighter being hit, and the opposite fighter's score increasing. For this to work however, we require a way for the status bar to know the collision has happened, although until now, we've had no way for the status bar or the fighter entities to communicate and share data with each other. As the GameState object lives over the top of all our entities and scenes, let's go ahead and see how that helps us here. We'll start off by adding some new values to the battle constant file. The first is the maximum hit points a fighter should have at the start of each round. This is a value of 144, which funnily enough also equals the number of pixels in length for each of their health bars. The next two are hex colour values, which we'll use to draw the health bar itself. The first one is for the remaining hit points, which is the yellow colour, and the second is for the damage points, the red colour. Back in the fighter state module, we'll also add a new property called hit points. This will store the fighter's remaining health. Initially we'll set this to the max hit points constant value we've just set up. Okay, let's move on to the status bar class and make the necessary changes to allow for the health bars to be updated. We'll first add the local property called health bars, because why not? This will be an array of two objects, one for each health bar. It will contain two properties itself, one for a timer to help for its animation, and one to hold the value for the hit points, which will go ahead and again set to the max hit points constant value. You might be asking why we're holding the value for the health and hit points here as well as in the game state object. We'll come back to that in a second, but let's update the draw health bars function to continue. Here we're going to lean on the canvas's context drawing function routines, as we'll be using them for the damage selection for each health bar. These will be drawn on top of the health bar image frame to the required size, based on the local health bars array property we just set up. So we'll start by setting the fill style to the damage constant colour. Then we'll begin to draw a rectangle with the context fill rect function. If you saw the second part of the video in this series, you'll remember we need to call the begin path function first, to ensure the context knows we're starting a new draw routine. The fill rect function is perfect for our needs, as it simply draws a filled rectangle to the canvas. It requires 4 parameters, the x and y coordinate values, which is the top left hand corner starting position, and a width and height value, which are the size of the rectangle. We'll define the left health bar first, as it's the easiest to draw, using the first object from our new health bars array. Its x position is 32 and its y position is 21, easy enough. For the width however, we'll be subtracting the hit points value from the max hit points constant value. So when the hit points value decreases, this will give us a difference and therefore its width. We'll again wrap this in a math.floor function though, to remove any unwanted decimal place we may have, whereas the height of the rectangle on the health bar will be just 9 pixels. For the right health bar, this follows the same format but does require a little more effort on the x position. As this is the starting position of the rectangle, this will always be moving to the left as the hit points decrease. So we'll take the left side of the right health bar as a starting x value, which is 208, and then add the hit points value to it. This will mean it will start to the furthest right, but gradually move to the left as they decrease. The y, the width and the height values are the same as the previous fill rect call, but obviously using the second object in the array. To prove this is working as intended, let's go back to the health bar's local property and amend the values a little. I'll use a value of 100 for the first or left health bar, and 30 for the second or the right health bar. With this, let's quickly see what the result looks like in the browser. And as you can see, the health bars are now correctly showing the damage based on the hit points applied. Okay, let's revert those changes back and look to get them decreasing automatically, based on the game StreetFighter hit points instead. We'll create a new function called update health bars to follow our usual naming convention, and call this within our main update function. Inside this new function, we'll iterate over the health bars array with a for loop. You may prefer to use the for each array function here instead, but I prefer to keep using actual for loops for my gaming projects due to the speed benefits they provide. Either way, we'll first compare the health bar's hit points property value against the game state's fighter hit points value. We know they both start with a max hit points constant value, so when they both have the same value, we'll not proceed, and therefore skip this iteration with a continue statement. Although if they are not, we'll use the seconds passed value multiplied by the FPS constant value and deduct that value from the hit points value. We're using the FPS value as we want the hit points to decrease by 1 every game frame. We'll also wrap it within a math max function to ensure it never goes below 0 too. Before we rush back to the browser, let's look to get our scores working with the global state object as well. In the draw scores function, we'll simply swap the hard-coded values of 1 we have for both fighters and use the game state fighter score property instead. To prove that both of these changes are working too, we'll first jump over to the fighter state module file and change the hit points property to a number less than the max hit points value. I'm using a value of 30 here. When checking the results in the browser now, notice that every time we refresh the page, both health bars will slowly decrease from the initial value of 144 down to 30, similar to the effect we have in the original game. Also, we don't seem to have any issue with the score either, as they still show the default value of 1, but this time these values are coming from our game state object. Great stuff, everything looks to be working as intended. Moving on then, and to the actual task at hand for today's video, we'll get the fighter's attack collision working with both the hit points and the score values within our game state object, which in turn will now affect the status bar entity as it's using those values too. But first, we'll revert back the hit points value and open up the fighter's constant file so that we can add a couple more objects to help us with the details. We'll first create a new enum object called fighter attack strength to hold the level of strength for each attack. Similar to the attack type enum object we created in the last video, we'll be adding this identifier to each of the attack states in the state machine. Although, before we do, we'll add another lookup object called fighter attack base data that will use these identifiers as keys. Each property will have an object of 2 properties, a score value that will be rewarded for the hit, and a damage property value that will hold the base value and will be deducted from the receiver's hit points value. Jumping back to the fighter class, we'll next add the new property to each of the attacking states within the states object. We'll call this attack strength and assign the necessary fighter attack strength value. We're adding this property here to ensure we know the strength of each attack. For example, we'll use this in the collision check so that we can determine the amount of damage to apply to the opponent's health. Okay, with these changes now in place, let's go back to the update attack box collided function and make the necessary updates to the game state object using this new data. We'll add two new lines, one to update the score and the other to update the opponent's hit points, as you can probably expect. We'll add local strength variable too, to get the attack strength as a shorthand. We'll quickly check the browser again, and whereas the health does decrease and the score does increase, it's unfortunately far too excessively. This is because we're not checking for the collision once, but actually on every frame. This means we're unfortunately responding multiple times, which is not what we want at all. In fact, you may have even noticed this before now with the console message, as this prints multiple messages too, highlighting the same unwanted behaviour. Not to worry, let's quickly fix this. Back in the fighter class, we'll add another local property called attack struck, which will default to false. This variable will be used as a flag setting, and will be set to true when an attack has been struck. We'll do this at the bottom of the update attack box collide function, but we'll also add another check in the guard clause to ensure that it's false, meaning the function will return out early if it's true, and therefore an attack has already been registered. Finally, we'll add a return statement too, so that we abort any further collision checks, as we know we've already responded to one. Lastly, back in the handle idle init function, we'll reset the attack struck variable back to false. Ideally we put this after each attack once it's completed, but as we know, once the attack has completed, the fighter will always go back to the idle state initially, so we'll leave it here for now. So checking the browser now, and thankfully we're working as intended. The collision has only triggered once, meaning both the health and the scores are responding correctly. Also, the collision message is only printing once to the console now too. Okay, all good so far. The last thing we're missing in regard to the health bar is the KO sign or icon in the middle. This would normally flash when either of the health bars go to a certain threshold, so let's look to add that next. We'll start in the battle constant file and add a few new values to help us with the code. The first is the animation delay values, used between the white and red KO frames as it flashes. Referring to the original game, we know the white KO frame is on screen for 4 frames, and the red KO frame is on screen for 7 frames. Although just as we've done previously, we'll need to multiply these values by the frame time constant to get the actual time delay. Next we'll add the animation frames array, starting with the KO white frame we already have, but also the KO red frame we've yet to define. So back in the status bar class, let's correct that and add this new key and frame details to the local frames map object. We'll also add 2 new local properties to allow us to control the animation. These are the KO frame to hold the animation frame index, and KO animation timer to hold an instance of the current canvas frame timer value. To implement the flashing animation, we'll first update the draw health bars function, and change the static KO white frame string with the KO animation array instead. We'll use the local frame property as its index, more on this in a second. We'll also deduct this property from the draw frame's Y position too, as this will match the movements in the original game also. The reasoning behind these changes will become more apparent as we create the update KO icon function, which will be called from the main update function. Inside this function, we'll first declare the animation, which ultimately is just the KO frame property, flipping between 0 and 1 on each frame change. As per usual with animations, we'll also store the time's previous value into the other local property recreated, KO animation timer. For the animation to work as intended however, again as per usual, we'll compare this property with the game's time value, but use the KO flash delay array value combined with the KO frame property as the index. This ensures we're using the correct delay for each frame. We'll simply return early though if the current time is less than the frame delay, preventing the animation from taking place. Now we just need to check that each health bar is below a certain threshold, because again, if it's not, we can simply return out of the function early. Although, what is this threshold value? Back in the battle constant file, we'll add a new constant called health critical hit points to follow our naming convention, and give it a value of 45, and then use that in the compare section of the function. This means that if either of the health bar's hit points go below 45, the KO sign will start to flash. Let's prove this with another check in the browser. And this seems to be working just fine. As we keep damaging the fighter, their hit points decrease, and as soon as it's less than 45, the KO sign flashes as intended, using the animation values we've defined. Perfect. I feel we've not given the fighters much attention in this video, so let's move on to the last thing for today, the hit splashes. When an attack has collided in the original game, it will indicate this by displaying a decal animation, usually called a splash. This varies by size and colour based on who got hit, and by the strength of the attack. So player 1 has a yellow splash, while player 2 has a blue splash. Also light attacks have a smallish splash, while the heavy attacks have the largest. Now that we have our battle scene class set up, it should be easy enough to add these to our game too. We'll obviously need a new image for these graphics, although we have a slight issue here. Our usual trusted source for Street Fighter 2 images, the Sprite's resource, does not have these sprites available, so I thought I'd properly prepare for this by extracting the necessary graphics myself from the original game, and submitting an entry to their database in advance. Unfortunately, at the time of writing, this is yet to be approved, so I am unable to direct you to their site for this part of the series, at least not yet. Hopefully whenever you're watching this has changed however. Either way, I'm showing the image I created here, where I perform the usual steps by dropping it into the images folder and naming it decals. We'll also go ahead and add an image reference to it within the HTML file, using an img tag along with the same alt attribute name. We'll now go into the Explorer window and create a new folder inside the Fighters folder, called Shared. This will house all the entities that are shared amongst the fighters, including the new hit entities we're about to create. So let's create a new file called HitSplash and jump into its code. This will be a standard entity class, but like our fighter class, it will be a superclass, where the splashes based on strength will inherit from. We'll start with the constructor as per usual, which will take a starting X and Y position coordinates, and a player ID, which will be used to determine which colour of splashes we'll use. We'll add these to local properties and also add an image property, with a query selector to pull in the new image data. We'll also add an empty frames array, and the usual animation properties too. And before we move on, we'll create the standard update and draw stub functions which are required for any entity class. With the basics of this class in place, let's now create another new class for the Light Hit Splash, aptly named Light Hit Splash. As mentioned, this class will extend from the Super Hit Splash class, meaning in the constructor we'll first need to use the super call and pass on any required arguments. If you're not familiar with inheritance, I'd highly recommend you look at part 3 in the series, where we delve into this a little more. Either way, we'll move on to the frames property and define the animation frames for the entity, which includes both the blue and yellow frames. Following our convention, we'll add a small comment above each section to identify which is which. Notice how we're not using the map object here, as the animation for these entities is a simple start to end sequence. For that reason, I didn't think it was necessary to have the overhead of frame keys, although if you wish, you can still add them here. We're still using the same array approach though, for the frame dimensions and origin position. Before we move on, we'll set up the update and draw functions, which will simply just call the superclass, passing on the required dependencies. So to keep this aligned, we'll update the main Hit Splash class with these two. Hopefully you can see we're simply using these inherited splash classes as a container to hold the correct animation frame details. The superclass will ultimately be doing all the work, as this is consistent across all the Hit Splash classes. So knowing this, let's look to complete the superclass, starting with the update function. We're simply following our usual animation convention here, using the animation frame and animation timer variables, using a delay of 4 game frames, which again is multiplied by the frame time constant, to get the correct time delay. If this period of time has passed, we'll progress the animation frame by 1, before resetting its timer for the next iteration. As for the draw function, we first need to deconstruct the necessary details from the frame array, based on the animation frame property. Notice we're using the player ID here as a modifier, and multiplying it by 4. This is so we can get the correct set of frames based on the player ID, because as we know, the first 4 frames are for the first ID, while the last 4 frames are for the second ID. Lastly, we'll call the draw frame function with the deconstructed dimensions and origin variables, and draw the splashed entry to the context. Let's now do the same for both the medium and heavy hit splash entities. Not sure if this was any quicker, but I decided to create 2 copies of the light hit splash class, and amend as necessary. Either way, we should end up with 2 new files named medium hit splash and heavy hit splash, along with the same class name inside. One addition here is that I've also added an index file too for the imports. If you're not familiar with this concept, it's a common front-end file management convention designed for convenience. It's out of scope of this video series, so I won't go into too much detail here, but for our example, as we have multiple files we're likely to import, rather than importing them from each individual file, you can group them together within the index file, meaning we'll just need one file reference, which is usually easier on the eyes, and generally easier to manage. Anyway, once ready, we'll now update the frames property in these 2 new classes, with the correct frame details. As per usual, I've got these already prepared, so I'll simply copy them over. Please pause the video if necessary. Okay, with the hit splash entities now set up, we need a way to instantiate them. Back in the battle scene class, we'll now use this entities array, and add any instances of them there. So let's create a new function called handle attack hit. This function will be used as an event handler, which will be triggered when a fighter has been hit. It will take a player ID, an opponent ID, a position, and a strength argument. But before we go into explain what these are, we'll first move the recent code we added to the updated attack box collider function in the fighter class over to this one, as it makes sense for this code to live here now. As we don't have access to the fighter class's local properties anymore, we can replace these with the corresponding function arguments instead. These take care of the score and hit point actions, so let's move on to the hit splash entity. We'll create a new function called addEntity, which will be a generic function to add any entity-based class to the entities array. For this reason, it takes an entity class and a set of arguments as parameters. Notice we're spreading any passed arguments into a variable called args. Inside this function, we'll now push to the entities array a new instance of the entity class we passed in, and again spread the args back into this class for its constructor. This concept might be a little difficult to grasp at the moment, but we'll explain it more as we continue on. Next, we're going to create yet another function called getHitSplashClassEntity, which will take a value from the fighter attack strength enum object and return the necessary hitsplash class based on the corresponding key. Just like the getFighterEntityClass function we created earlier, this will be a switch statement, listing the correct matchups. We'll again throw an error if an invalid strength value has been passed in. Back in the handleAttackHit function, we can now call the generic addEntity function and call the getHitSplashEntityClass function to return the correct hitsplash class based on the strength property we've passed in. We'll then pass on the individual x and y values from the position argument, and lastly the player ID. This should add the correct hitsplash entity to the entities array, which in turn will be added to the usual update and draw calls of the battle scene as it loops over that array. The next step is to initiate the handleAttackHit function, which we know needs to come from the updateAttackBoxCollider function within the fighter class. As this is an event handler from the battle scene, we'll pass this function onto the fighter class as a callback. So in the getFighterEntity function, when we create a new instance of the class, we'll pass on this function here as a new argument, remembering to bind this to it. So we'll now need to update the fighter classes to recognise this new callback event handler function. We'll add the onAttackHit parameter to the constructor and create a local property too to hold a reference to it. Then back in the updateAttackBoxCollider function, we can now call this callback and pass on the necessary arguments. Although we're missing one, the position, which is used for the hitsplash entity. As we know the collision details at this stage, let's use those with a little bit of maths to figure out where the hit splash should be positioned. We'll create an object with x and y properties called hitPosition. To get these values, we'll take the hitbox and hurtbox dimensions and find both of their centres by dividing their widths and heights by 2. The widths for the x position and the heights for the y position. We'll need to add the original hit and hurtbox's x and y position to these as a starting position. Then we'll work out the centre position of those by again dividing the results by 2. Phew, okay, this should give us a good base position for the hitsplash entity. However, we're still not finished. The original game added a little bit of randomness to its position, so let's also do that too. I decided to use a random value between -4 and 4, giving us a variation of 8 pixels. To do this, let's deduct 4 pixels, and then deduct a random number between 0 and 8 from that, applying this randomness to both the hit position's x and y values. Finally, we can now complete the onAttackHit call by passing on this value as the missing argument. Before we move on, let's not forget to update both Ryu and Ken's classes too, as we'll need to add the onAttackHit parameter to each of their constructors to ensure it aligns to the fighter class. We'll also jump back to the battle scene class to fix up the imports, first with the fighter attack base data, and then we'll put our index file we set up to use for the splash hits, trimming down the free imports VS Code automatically added to a one-liner. And with that, we can now finally check the browser to see what we've managed to accomplish. And unfortunately we have a problem. Even though everything does indeed look like it's working, with the splashes appearing as intended when the attack collides, but unfortunately it doesn't have an end or death event, so it attempts to continue to animate beyond its 4 frames and causes a crash. We can prove this by bringing up the debugger and checking where the error is located. Okay, let's look to fix this in the last change for today's video. Below the addEntity function, we'll create a new one called removeEntity. This is another generic function that basically does the reverse of addEntity, as you can expect. It takes an entity reference as a parameter, which we'll use inside an array's filter function. This will return a new array with this entity removed, and assign it back to the class's entity array. Probably not the most efficient method, but for the amount of entities we're using, it shouldn't be much of an issue. Similar to what we're doing with the fighter classes, we'll next add this to the addEntities function's entity class arguments. This applies a handy contract to any entity, providing it with this removeEntity function. Again, we'll have to bind this to it to keep it in the scope of this class. We can now go into the hitsplash classes and add this to their constructors. We'll start with the superclass, hitsplash, and add an onEnd parameter and continue to assign it to a local property with the same name. We'll now add a simple check within the update function to check if the animation frame is equal or higher than 4. which we know is the end of the animation, and if so, we'll call the onEnd function. This obviously results in the splash entity being removed from the scene's entity array. Let's now continue and add the onEnd parameter to the remaining kitSplash classes, forwarding it on within the supercall. So, with another check in the browser now, we can go ahead and attack as much as we want, using any of the available moves. The hitSplash entity is removed from the scene when the animation has completed, fixing our recent crash issue. Great stuff, and with that, I think we'll move on to our final section of our videos, refactoring. We'll start with a couple of easy ones. The first is in the battle scene class. We currently have a couple of main entities being instantiated in the constructor. This is fine for our purposes, but let's move these into their own function called startRound. As you can gather from the name, this function will be used whenever we want to start a round, so it makes sense to house any code here that needs to be reset when each round has started. This will mostly be explored in future videos, but for now we'll move the fighters, camera and shadow over to this function. Once done, we'll call this new function within the constructor. Next, we'll now move the shadow file from the fighters folder over to our new shared folder, as it makes sense to live there now. We'll then update the index file so that it's available to import just like the hit splashes. Back in the battle scene class, we can now simply extend the one-line import with the shadow class, removing the need for the original import. Nice. While on the topic of index files, let's do the same for our fighters too. We'll create a new file, again called index.js to follow convention, and export both the Ryu and Ken classes here. Back in the battle scene class, we can now consolidate both of their imports and use their index file too. Okay, let's now move to the status bar class and make a few things more consistent. We'll start with the battle constants, moving them into individual lines as they're getting a little long. Next, we'll move down to the drawScore function to make a quick optimization. At the bottom of this function, we're iterating over the score string and drawing the individual frames to the context. However, in the function below, drawScoreLabel, this already does that, so let's remove the current code and use this instead. We'll also change the str value and the buffer variables to strscore and padding respectively, as I feel they give a better description. We'll then move the drawScoreLabel function above this one to keep the calling order in sequence. Next to the battle constant file, we'll now update the time delay and time flash delay values to use the corresponding frame value and the frame time constant value instead, again keeping consistency. We'll now update the constructor and the local properties with a new convention, which you may have seen we're already doing in the StreetFighter class, defining the default properties and their values outside of the constructor and at the top of the class. This removes the noise from the constructor, giving it clear responsibility of just setting up the variables based on its parameters. It also allows us to remove the this prefix from any other properties, making it much easier to read. We'll apply this convention across other classes over time as we refactor them. The last couple of refactors for today will be for the fighter class, starting with moving the debugging code over to its old module file. So in the Explorer window, let's create a new file called FighterDebug, and move the drawDebug and drawDebugBox over to it. We'll then add a new function here called drawCross. This function will contain the white origin cross we currently have below, but we'll put it here just to keep this module a little more clean. This function will take context, camera, a position and colour arguments. So we'll make just a few adjustments to the code, first changing the hard-coded white colour to use the colour argument, and lastly removing the this keyword which is no longer used. For the drawBox function, we'll amend its parameters to use a position and a direction, but also amend the base colour parameter to be colour instead. Again, we'll make the same adjustments here, matching the new parameter changes. And finally for this module, for the main draw function, we'll rename it to debug draw collision info and allow it to be exported. I've made the debug prefix capitalised, so it's obvious that it's just a debug function and should really not be used outside of development. We'll then add a fighter parameter to it, as we'll be passing this on from the fighter class, quite literally. So we'll replace the current code at the top to a single set of deconstructed variables from the fighter argument. We'll then amend the remaining code to use the new position, direction and boxes variables, and call the above box and cross functions instead, not forgetting to call the drawCross function too, and removing any of the unnecessary comments also. Now back in the fighter class, we'll replace the current call with a new function instead, passing on this as the first argument, which will be the fighter instance. Now back at the top of the class, we'll import this function from its new file, and while we're here we'll also remove the unused fighter attack base data reference too. And lastly, we'll apply the same constructor convention to this class as we did with the status bar class, moving all the local properties to the top of the class, where they are not referenced by the constructor arguments, removing the this prefix for those just like before. With all the changes made, the constructor should now just contain the player ID, position, direction and the change state call, again making it easier to see and manage the class's arguments. With that, I think we're finally done for today. Okay, let's have another final check in the browser and see if the game is still working as intended. And thankfully, even after all that refactoring, it looks like nothing is causing us problems. Both Ryu and Ken can continue to attack their opponent, and the health bar, score and hit splashes all seem to be working correctly based on the attack strength. So let's quickly recap what we've accomplished in today's video. The game has moved considerably forward, I feel, in this video, especially as we're starting to polish up the code and preparing it for the changes to come. Finalising our first scene, the battle scene, means we can now go in and add any number of the missing scenes with ease in theory, even more so as we now know how to share data between them, either with the global or local states via events. We could go in and extend this further and add an event system, but that's maybe one for another day. As for the game itself, the status bar is very near completion, as it reacts and functions very close to the original game, now that we have the health bars, scores and KO icon all working. With the fighters themselves, we finally managed to improve the collision by adding the hit splashes to the attacks. This provides some good feedback for the user, but we're not finished there yet. We'll look to expand on this even further in the next video, by adding the stun and attack states. We'll also hopefully add the crouch and jump attacks too, if we get time. Although for the main topic in part 12, we'll start exploring the music and sound, using the web audio API. I feel we're deep enough into the project and game now, it's feeling a little too quiet without it. So we'll look to get the stage background music in, and any of the fighter sounds where possible. Something different, I suppose. So it looks like this video is again the longest one to date. I hadn't planned for the videos to keep growing in length, but it seems they always do naturally on their own. Hopefully people don't mind this too much, but appreciate that longer videos aren't everyone's bag. Let's see if I can correct this in the next part. Which leads me on to the updates I posted on my various socials this past month. Hopefully everyone has seen them, but if not, I posted the schedule of the remaining videos in the series. I've begun to notice the view count has been diminishing recently in the last few parts, which I assume is just natural for a long-running YouTube series. Although I will be looking to finish off what I originally had planned, but then I'll more than likely be moving on to new content for the health of the channel. That said, we have at least 2 videos remaining. The next one will cover music and sound, and the last one will cover special moves, both of which should be dropping in the following months, leading into spring. I do feel we still have content to cover in the series beyond the remaining videos, so I'll no doubt come back with a smaller second set of videos later in the year. I plan to do something different in between, more news on that soon. And just before we close up for today, I'd again like to thank everyone for their support. It's extremely staggering that I have over 500 subscribers now. I honestly would never have thought that was even possible. So thanks again for all the likes, comments and subscriptions you may have contributed to over the last 6 months, both on this channel and on my Patreon page. Finally, a big shout out to all the Patreon supporters here. You guys are the ones who spur me on the most. And with that, I'll say my goodbye and hopefully see you in the next one. And out.